Hello and welcome back to another Unarculus production. Today we are going to talk about the beginning of chapter 3, okay, which will take us through the extreme value theorem and the mean value theorem. All right, a couple of new theorems here to talk about. Before we get started, let's talk about what our goal is in this chapter. Okay, the goal is actually pretty simple. All right, it's a simple concept to take a look at. So the goal of this chapter is to graph any curve without a graphing calculator. Okay, so the goal here is to graph any curve without the use of a graphing calculator. So quite a lofty goal for just 6 sections worth of work. Okay, the idea is what we're going to learn in the first 5 sections are pieces of information that we can get from the equation and its derivatives that will help us to then create a graph, which we will then create in section 3.6. Okay? All right, so let's get started on finding these pieces of information. All right, so the first thing we got to talk about here is a couple of things that you already know. Local or relative extrema. Local maxes, local mins. All right. So the idea is pretty simple. You've done this before. Okay, here's a graph. I could draw f of x. There it is. All right. This graph, okay, local maxes are where the graph changes from increasing to decreasing, right? So that would be this point here and this point here. So we'd call these 2 points relative or local maximum. All right. Now, these 2 words, relative and local, are used interchangeably. Some books call them relative maxes. Other books call them local maxes. Okay. On the exam, they're also used interchangeably. You do have to know what both of them mean, that both of them refer to the same thing. All right. Now, this point down here is where the graph changes from decreasing to increasing. This point is a local or relative minimum. Okay. Now, an important thing that you need to know, all right, an important thing that you need to know about local maxes and local mins is that they cannot occur at an endpoint. Okay, they will try to trick you with this on the AP exam all the time. They love to do that. So what I'm saying to you is the following. If I have a graph and the graph ends, okay, or has closed circles on a closed interval, neither one of these points can be referred to as a local max or a local min. The reason being, you just don't know what happens on the other side of this point. So for example, if the graph were to turn like this, then yes, this point would be a local minimum. But if the graph continues to decrease after this point, like that, well then this point is a nothing, right? It's certainly not a local min. Okay, so local mins and local maxes cannot occur at endpoints. Local mins or local maxes are traditional mins and maxes, where the graph changes from increasing to decreasing for a max or decreasing to increasing for a min. All right? Okay, so let's keep going, because let's introduce something that maybe you haven't seen before. Absolute or global extrema. The concept of an absolute maximum or an absolute minimum. Okay, so if I have a graph and I call it f, and it looks like this, let's say, I have at this point a relative max, at this point a relative min, at this point a relative max. So that we just learned in the last slide, right? You already know that. Now, the idea of an absolute min or an absolute max is that it is the highest or the lowest y value, okay, on a specific interval or on a given interval. So this point is the relative max, but It's also the absolute max, right? It is the highest y value on this graph of f of x. This point happens to be the end point. It's not a relative min, because I don't know what happens after it. However, it is the absolute min, because it is the lowest y value on this graph. Okay, it is the lowest y value. The y value will never get lower than this point. So absolute mins and absolute maxes can occur at the endpoint. Okay, they can occur. They don't have to, but they can. All right, and that's important to understand. All right, let's see what we have. So now let's just fill in this little graph that we have here with whether or not things are local, absolute, whatever they are. Okay, so let's start over here. This is a local or relative max. We'll call it local on this slide just to get the idea that they're both the same. There's a local max. Point C is a local min. Right? Point D is the absolute max. It's also a local max, right? In the traditional sense, it's where the graph changes from increasing to decreasing. Okay? Point A is the absolute min. It is the lowest y value on this interval. And point E is just an endpoint, right? There's nothing going on here. It's not an absolute min. It's not an absolute max. Okay. Now, it certainly looks like it potentially could be a relative min. We agree, but it's an endpoint. It cannot be a relative min. I don't know what happens after this point. Okay. I don't know what happens after E, so I cannot say that it's a relative min for certain. All right. Now, this star here, okay, this point that the star is at is actually an important point, and we're going to talk about it later on in this chapter. But you can see at this point that the star is at, the shape of the curve changes, right? It looks like the shape of the curve is actually changing. The graph is still kind of increasing, right? The graph certainly still looks like it's increasing, but the shape of it is different. And we will talk about that later on in this chapter, what that point is and what it represents. Okay? All right. Now, let's talk about extrema at corners and cusps. So if you take a look at the graph that we have here, we'll call it F just to call it something. Okay? We have 2 points here. Well, actually, we have a point here that we know definitely is a relative max. All right? As well as these other 2 points where there are corners and or cusps, however you want to call it. Okay? This point is certainly a relative max, right? It is certainly a relative max. Okay? It's where the graph changes from increasing to decreasing. Same thing here. This point is also a relative max. Or I'm sorry, it's a relative min, right? It's a low point. Okay? It's a relative min. It's where the graph changes from decreasing to increasing, right? Going down to going up. All right? Now, the one thing you can notice about these points that will be important momentarily, okay, is there's something weird going on here in terms of the derivative, right? Because they're corners or cusps. We understand things about things that are corners or cusps. Okay? We know that they're not differentiable, right? Graphs are not differentiable at those points, which means the derivatives will be undefined. All right, so there's something weird going on, but they can still be relative mins and relative maxes on the graph of f, even though there's issues with the derivative. Okay, so let's get to kind of the heart of the matter here, at least for today. If you were given the equation of a function instead of the graph, how would you find the relative mins and the relative maxes? So that's the question on the table here really today. How would you find mins and maxes if you were given the equation of a function instead of the graph of it? All right. So what we can do is we can look at a graph, okay, because that'll help us to determine where the mins and maxes are. All right. So if we look at this graph, you can certainly see there's a relative max there, a relative max there, and a relative min there. Now the question is, what do all these points have in common? Well, if you remember back from the last chapter, excuse me, if we call this f, okay, this function f, these were the first points that we looked for because we already knew the derivative's value there, right? We know the slope of the tangent line at these points are all 0. Okay, so that meant that f prime of x must have equaled 0, right? And that's what we graphed. Okay, so the slope of the tangent line here is also 0. That means f prime is equal to 0. Same thing here. The slope of this tangent line is equal to 0. So f prime is equal to 0. Okay, so it looks like if we were given the equation of a function instead of a graph, it looks like what we'd have to do is to set f prime of x equal to 0, right? Because that would tell you whether a point potentially would be a min or a max, right? If the x value would potentially be a min or a max. Now, it wouldn't distinguish which one it is, right? It would just give me an idea of where it might be, that min or max, not whether it's a min or max. So that's something else we have to determine also, right? Something else we have to be concerned with, okay? Now, there's another place where you might be able to find mins and maxes, and that was based on the last slide that we just talked about. So, for example, I have, let's say, an absolute value graph, right? Well, that point here, okay, is certainly a relative minimum on this graph of f. But if I find the derivative is going to be undefined here because f is not differentiable at this point down here, right? F is not differentiable there because it's a corner, okay? So f prime will be undefined. So the other place that you can find relative maxes and mins is to set f prime equal to undefined, right? Figure out where f prime is undefined, okay? That will also be places where potentially you could have a min or max. No guarantee, but potentially, okay? All right, so those are the two things that we're really going to use here. And if you look at the next slide, we actually have a special name for that. If f prime of c is equal to 0 or f prime of c is undefined, then x equals c is called a critical number of f of x. Critical numbers are, again, potential relative mins and relative maxes. They're not guaranteed to be a potential min or max. I'm sorry, they're not guaranteed to be a relative min or relative max. They're just potential relative mins and relative maxes. Okay, we have to determine how we would figure out which one they were if they were either one. And we will do that as we go along in chapter 3. But let's start with a simple example here. I want you to find for me any critical points of this function, f of x equals x squared plus 4x minus 5. So to find any critical numbers or critical points, you need to find the derivative of this function, which would just be 2x plus 4, and set it equal to 0, or set the denominator equal to 0 to see if it were undefined, but there's no denominator. So we can solve this pretty quickly, and we get x equals negative 2. Okay, x equals negative 2 is a critical number of f of x. That means at x equals negative 2, there's a potential relative min or relative max. Okay? Now, they also can ask you for a critical point. A critical point is obviously an x and a y paired together, right? It's an ordered pair. To find a critical point, you're going to take the x value, x equals negative 2, and you're going to put it back in the original f of x. Because remember, the one thing you should never lose sight of in this chapter is the goal is to graph f of x when we're all done with it. So if we're going to get any points that have an x and a y, we want to know what f or x is and then the y value in f of x, because we want to graph that point. That point is probably important. All right, so if we just clean this up, we get negative 9. So we could say negative 2, negative 9 is a critical point of f of x. Okay, so basically they mean the same thing. All right, Critical points are good because we're going to eventually go graph -2, -9, okay, if it is a relative min or relative max, and then we can label it. All right, because ultimately we're trying to make a graph. Okay, all right, so that's the first example there real quick. Now let's do the same thing. Find me all critical numbers of f of x equals 4x over x squared minus 1. So now I need to find the derivative, set it equal to 0, okay? But this is a quotient rule problem. So let's go do that. It's ODI minus IDO over OO. There we go. All right, so let's clean this up. We have 4x squared minus 4 minus 8x squared all over x squared minus 1 squared. So that's going to give me negative 4x squared plus 4 over x squared minus 1 squared. Okay, so if you want, you can either factor out the negative 4, it's in common in both, or just set the top equal to 0 to find the potential critical numbers there and solve it that way. It doesn't make a difference. So there is your derivative. So now the first thing I'd want to do is figure out where, set this to 0. So if I want f prime of x to equal 0, that means the numerator would have to be 0. But that's not going to happen, right? So that would mean x squared plus 1 would have to be equal 0, but it doesn't. So you don't get anything from that. Now, the other question is where f prime of x might be undefined. Okay, that would mean the bottom would be 0. All right, so we can just get rid of the square and just want to know where x squared minus 1 equals 0. That's at plus or minus 1. So these are critical numbers of f of x. All right, now you can see that probably that they're not going to be mins and maxes, right? Because if you try to plug -1 and +1 back into the original, you're going to get 0 on the bottom there. So they're going to be vertical asymptotes, but they are considered to be critical numbers. They are potential relative mins and relative maxes. Now, in this case, it turns out that they don't end up being relative mins and relative maxes, but if you're asked for critical numbers, which you will be occasionally on the exam, it does count as a critical number. Both of them, okay? All right, so let's talk about the first theorem as promised, which is the extreme value theorem, okay? The extreme value theorem is another if-then statement. There it is, all right? If a function is continuous on a closed interval, AB, then it must have a minimum and it must have a maximum on the interval, okay? So it's a pretty simple theorem to think about. Here's a closed interval, A, B. There's something that's continuous. This does have a min and max. It has an absolute min at A. It has an absolute max at B, right? There's no relative mins or relative maxes. It just has an absolute min and an absolute max, okay? It's guaranteed to have an absolute min and an absolute max somewhere. Here's another one. Oops. Too far. Too far on that. All right, let's go to B here. So this point up here is a relative max. It's also the absolute max, right? And then B is the absolute min. It's the endpoint, okay? But what about this? That's certainly continuous. Does it have a min and a max? The answer here is yes, it does. Every point is a min and a max, right? Every point's the absolute min and every point's the absolute max because all the values are the same, okay? So that's what we're talking about here. If a function f is continuous on a closed interval AB, and again, the interval has to be closed, okay? If the interval is open, then the theorem doesn't hold. There's an absolute max over here at A. The question is, where would the absolute min be? But there is no absolute min. right? If I were to call this, let's say, I don't know, 4, just to put a number on it, right? What is the x value at which there's an absolute min? Well, it's not 4 because you can't stand there. Okay, there's no point there. It's not x equals 4. Is it x equals 3.9? No, because it could be 3.99. So, but then it could be 3.999. Then it could be 3.99999, right? So we're never actually going to reach, okay, a specific value at which there is a point, or that we can say for certain is the absolute min. So the extreme value theorem does not hold. Okay? The extreme value theorem doesn't hold there because f isn't continuous on the closed interval. All right? All right, so now what we're going to do today is we're going to find absolute mins and absolute maxes on a closed interval. Okay? So the first thing you're going to do to find an absolute min and an absolute max is to find the critical numbers, which we just did a couple slides ago. Find f prime of x, set it equal to 0, or where f prime is undefined. The next thing you're going to do is establish the candidates. Okay? Okay, the candidates that could be the absolute min or the absolute max. Now, we've looked at a bunch of pictures, right? We understand that the absolute min or the absolute max could be a relative min or a relative max. That's why we look at the critical numbers, because the critical numbers are where the relative mins and relative maxes could be, okay? But the absolute min or the absolute max could also be the endpoints. All right, so we're going to establish some candidates for an election. All right, appropriately, yes. Okay, this time of year, the candidates for election. All right, those candidates will be any critical numbers that you find as well as the endpoints. Okay, all of those will be candidates. All right, and then what you're going to do is you're just going to take those election candidates and you're going to plug them in to the original function f of x. Okay? And then finally, you're going to look at the y values. The largest y value is the biggest winner. That will be the absolute max. And the smallest y value is the biggest loser. They will be the absolute min. All right? And again, it doesn't matter if it's a critical number or an endpoint. Could be either one. All right, let's take a look. I want you to find for me the absolute min and absolute max of this function on that closed interval. Okay? All right, so first thing you need to do is find the critical points. All right, find the critical numbers. So let's find the derivative. We have 2x plus 2, set it equal to 0. You get x equals negative 1. Whoops, negative 1. Okay, so x equals negative 1 is a critical number. Now, let's talk about the candidates. The candidates for this election are the following. X equals negative 1. That's a critical number. X equals negative 2 is an endpoint. X equals 3 is an endpoint. These are your 3 election candidates. So now to figure out who wins, okay, you evaluate all of them in f of x. So f of negative 1 would be negative 5, I think. Yep, looks right. F of negative 2 is 4 minus 4 minus 4, negative 4. And f of 3 is 9 and 6, 15, minus 4, 11. So that means the biggest winner, the absolute max, is 3, 11. Okay? The absolute min is negative 1, negative 5. Now, in some cases on the exam, especially, they ask you for the absolute minimum value. The absolute minimum value, remember, when I say the word value, I want a y value, okay? It's understood that you want the y value. Absolute maximum value would be 11. The absolute minimum value would be negative 5. Okay, then they only want the value, not the point. All right, they only want the y value. Okay, so pretty simple, I think. All right, so one more here. So find the absolute min and absolute max of f of x equals the third root of x on the interval -1, 1. All right, so the first thing you have to do is find the critical numbers. So we're going to have to go and find the derivative. So f prime of x is 1/3 x to the -2/3. So now I can clean that up a little bit. Right, I can put the x to the -2/3 in the denominator, and I get 1/3 x to the 2/3. All right, so the first thing that I can do is figure out if f prime of x is equal to 0, but that would mean 1 has to equal 0. That doesn't do anything. So f prime would be undefined if 3x to the 2/3 is equal to 0. So you can solve that pretty easy. X has to be 0. So x equals 0 is a critical number. Again, it's undefined there, but it's still a critical number. Okay, so now my election candidates are the following. X equals 0, which was a critical number. X equals -1, and x equals 1, which are both endpoints. All right, so now we're going to take all three of these, plug them in the original. F of 0 is the third root of 0, so that's 0. F of -1 is the third root of -1, which is -1. And f of 1 is 1. So the absolute max is the 0.11. The absolute min is the point -1, -1. All right, if I ask you for the value, absolute max value, it's 1. Absolute min value is negative. All right, and that's how this works. Okay, so you just find the derivative, find the critical points. All right, establish your election candidates, and then plug them in and figure out who wins. Okay, now the second theorem here is called the mean value theorem. This is going to be pretty familiar to you, I think. All right, so if you read this real quick, okay, you go on a road trip, right? You're driving along, and at noon you enter the toll road, and you start at mile marker 1. Okay, Cape May, I guess, right? Mile marker 1, Cape May. You notice that the speed limit is 55. At 2 p.m., 2 hours later, right, from noon, you exit the toll road at mile marker 141. You exit and hand your ticket, the attendant your ticket, and then it's $5 for the toll and $125 for speeding. Okay? No police cars, no police cameras. Were you speeding? And how did the attendant know? All right. Well, first of all, you were definitely speeding, and I think everybody can see that, right? Okay, because what happened? At noon, all right, let's say noon will be t equals 0. So at t equals 0, you're at mile marker 1. At t equals 2 p.m., 2 hours later, you're at mile marker 141. Okay, so if you just find delta x over delta t, right, which is the average velocity, okay, or v bar, you get 141 minus 1 over 2 minus 0, so 70. So your average velocity was 70 miles per hour, and the speed limit's 50. So yeah, definitely, you were speeding. You were probably speeding almost the whole time. We agree? Okay, how did we do that? We found the average velocity. Now, what are we talking about here? First of all, you found the average velocity, and the average velocity was 70, right? Now, how did he know that you deserved a ticket? Well, he knew that you deserved a ticket because the speed limit was 55, which means that at least one moment in time on your trip, okay, on that 2-hour trip, you must have been going more than 55 miles per hour, right? Your instantaneous velocity at some time must have been more than 55 miles per hour, okay? So you deserve the ticket, all right? Okay, so now we're talking about, again, average velocity, instantaneous velocity. We did this in the last chapter. All right, so now let's do this real quick. Okay, let's graph a function that satisfies the following conditions. It has to be continuous on AB closed. Okay, it has to be differentiable on AB open. And f of A can't equal f of B. So let me do this. I'll go through the words too, but it'll be easier for you to see. Okay, so there is my graph there. All right, here's f of x. Okay, and we'll talk about this in a minute or two. Yeah, we'll definitely talk about this. All right, so now the question is, here's what I want you to do. Okay, there are 2 points on this graph, right? If I call this f of x, there's one point here at a comma f of a. Then there's another point here at b comma f of b. What I could do if I wanted to would be to literally connect these 2 points. Almost. Okay, and get myself some kind of secant line, right? Okay, if I erase the other pieces, the extra piece. There you go. There's my secant line, right? It's the line between 2 points. Okay, I can find the slope of that line, certainly, because I have 2 points. So the slope of that secant line is f of b minus f of a over b minus a, right? Delta y or delta x. Okay, y2 minus y1 over x2 minus x1. Now, my question to you is, can you find a place on this graph of f of x where the slope of the line, the orange line that I just drew, is the same as the slope of a tangent line somewhere along this graph of f of x? Now, I claim you can, right? Certainly looks like it. It looks like maybe here. I don't know. Maybe here. Looks like. Yeah, it's pretty close. Okay. I'm going to call this point C. So now, how would I find the slope of this line that's in pink? Well, first of all, we call this line a tangent line, right? So I would need to find the slope of the tangent line. To find the slope of the tangent line, I'd have to find the derivative. And in this case, I'd plug in C, because C is the x value that I said that point was at, right? Okay, so the slope of the tangent line is equal to f prime of C. And now I found a place where these two are equal to each other, right? I found a place where f prime of C was equal to f of b minus f of a over b minus a. This is the mean value theorem. Okay? This is the mean value theorem. All right, so now here is the little more fancy version. Suppose f is a function that's continuous and differentiable, then there exists a number c on AB open, such that f prime of c is equal to f of b minus f of a over b minus a. All right, that's one way to say it. You could say the slope of the tangent line is equal to the slope of the secant line. Okay, you can also say a rock equals I rock. That's really what the mean value theorem is all about. A rock equals I rock. Average rate of change equals instantaneous rate of change. All right, so now I do also have to talk to you about why f of x can be differentiable on the open interval AB and closed, continuous on the closed interval. Okay, so it's actually a pretty simple concept to understand. So certainly this graph is continuous, right, on the closed interval all the way through, as well as the endpoints, it's continuous, okay? But it doesn't have to be differentiable at the endpoints themselves. The reason being because simply you just don't know what happens before this endpoint or after this endpoint. So if, let's say, for example, at B, after we get through this point, the graph looks like this. Well, now there's a cusp here, okay? So the function, or f, would be undefined there, right? F prime would be undefined there, okay? F prime would be undefined there, all right? So we just ignore the endpoints, all right, as best we can, so that we don't have to worry about them. So we eliminate the fact that the function has to be differentiable at the endpoints themselves, because we don't know if they're going to be differentiable at the endpoints themselves. Okay, we just know that someplace along A to B is where the AROC will equal the IROC. All right, so that's why it's continuous on the closed interval and differentiable on the open interval. Okay, all right, so let's try a couple of these real quick, and then that's it. So first one, find the value C satisfying the mean value theorem for this function f of x equals x squared minus 1 over x on the interval -1 to 1. Okay, so the first thing you have to do here is you have to convince me. Number one, for the mean value theorem to work, f has to be continuous on -1, 1, closed. X is discontinuous, right? We know that x can't be 0. So is this function continuous on the closed interval -1 to 1? No. So the mean value theorem does not apply. I can't use the mean value theorem on this. This is one heck of a first example, right? Show you about the mean value theorem. You can't use the mean value theorem on this. F is not continuous on the closed interval -1, 1. So we're out of luck. Okay? No mean value theorem. All right. Let's go to the next one. All right. So now, same thing with this function on 3, 6. First thing, f has to be continuous on 3, 6 closed. Well, we can see up here that x can't be -1, right? Because that would make the denominator 0. But f is continuous between 3 and 6, and that's all I care about. I don't care about -1. Okay? Number 2, f has to be differentiable on 3, 6 open. All right, so to figure out if f is differentiable, I guess I'd have to find the derivative of this. So the derivative is, with the quotient rule, OD high minus ID ho over OO. And if I clean this up, I'll get 1 over x plus 1 squared. So again, x can't be -1, but I don't care. That's not between 3 and 6, so it is differentiable on 3, 6 open. All right, so both of these have been satisfied, so we can use the mean value. The mean value theorem just says AROC equals IROC. That's what it says. Simple. Okay? You did it in the last chapter. I just didn't tell you it was the mean value theorem. Right? You showed me where the average rate of change was equal to the instantaneous rate of change on some multiple choice questions. I just didn't tell you it has a special name. Okay? So let's find the AROC first. To find the average rate of change, we'll just find f of 6 minus f of 3 over 6 minus 3, which is, we have 6 over 7 minus 3 over 4. Really? I couldn't have picked anything easier than that. Okay, over 3. All right, so 28 would be the common denominator. So this would be a 24. Right, 24, and this would be 21. So we have 3 over 28 over 3. So that's keep this, divide by this. So keep this, change this, flip this over. So we're going to get, it looks like, 3 over 28 times 1 over 3. These cross out, 1 over 28. Okay, so the AROC is 1 over 28. All right. So now I'm going to erase this stuff here because I need the space. Okay, so now 1 over 28 is your AROC. So you know what your IROC is already. Your IROC is 1 over x plus 1 squared. So we want 1 over x plus 1 squared to equal 1 over 28. All right, so I would cross multiply. I have two equal fractions. So you have 28 equals x plus 1 squared. Take the square root on both sides and put plus or minus. Okay, x plus 1 and subtract the 1. You get x equals -1 plus or minus square root 28. Now, that's not the answer. Okay, there are not two answers here because remember, The value of C that's guaranteed is somewhere between 3 and 6. Okay? So negative 1 minus square root 28 is a negative number. So that number doesn't work. Right? So we're going to throw that out. And we're going to let C be negative 1 plus square root 28 only. Okay? It can't be negative 1 minus square root 28. That's not between 3 and 6. All right? And that's it. That takes care of the extreme value theorem and the mean value theorem. As always, thanks for clicking.